Hello everybody. Today's lecture is going to be on generators. This is the last module of electromotive force section, or methods of producing EMF section of the course. We're going to be talking basically about Faraday today, or we're going to be exploring that idea he had of a conductor cutting lines of flux, magnetic lines of flux that is, induces a voltage on the conductor. And we're going to take that idea, we're going to hook it up to some kind of circuit, and we're going to generate electricity. Now, generators, basically, almost all the generators, take mechanical energy and convert it with the generator and with Faraday's law, and we can learn more about what's exactly going on with, Fleming's hand and all that fun stuff. But a generator is going to take mechanical energy and convert it into electrical energy. So if you take a little two-stroke generator and you're using a two-stroke motor or engine to turn a little generator inside, that's how you use, let's say, internal combustion engine to turn the generator, to turn the armature, we're going to learn about, in order to create EMF. So the mechanical energy would be the two-stroke engine, or whatever kind of motor is turning the armature of the generator or spinning something. You could also use, big flows of water. That's how hydroelectric dams work. They have water, which is our mechanical energy. That's our input energy. And then our output is electrical energy. So the module calls our old friend Fleming's left-hand rule. It calls it the generator rule. Now, or the left-hand rule for generators, Now it works the exact same way. Finger points from north to south. It kind of follows the magnetic lines of flux with your index. Your thumb is the motion of the conductor. And then your middle finger, or your second finger, if you want to call it that, this finger, the one you use to wave at people in traffic sometimes, this is going to be the direction of current flow. So this module is a bit of a review of the last module, but it's going to use what we learned about magnetism and electromagnetism and Faraday and Fleming and all that fun stuff. It's going to use it specifically towards generators. So we're just kind of going over this again, where the movement of the conductor, if it's this way, and my magnetic lines of flux are going north to south like this, well, that means the current would be coming out of the page. I know my left hand doesn't quite communicate that effectively, but it's as if an arrow was coming at us, so current is coming out of the page if the conductor is moving this way. And then when the conductor moves the other way, the current's going to go the other way, because in this situation, our magnetic lines of flux are not changing at all. They're going to stay the same. They're kind of fixed magnets like this. So let's get into the real meat of the matter. This is a simple generator. Now, the things here that Faraday would really care about are these armature conductors and these, the field coils, really, because the field coils turn these pole cores into electromagnets, or our main source of magnetism comes from these pole cores that are around the armature. And the reason Faraday loves those two things is because when we spin this armature, when it starts a spinning from some kind of mechanical energy put in, these conductors are going to start to cut magnetic lines of force. And Mr. Faraday says, good, I love that. Make that EMF. Induce that voltage into the conductors. Now, the module kind of describes the two circuits that are involved in a generator. They talk about the magnetic circuit and then the electrical circuit. The thing missing from this diagram that's a part of the electrical circuit is what we're going to talk about called brushes. Now, brushes, quite simply, brush against these armature conductors or something that's connected to these conductors, and the brushes basically take that electromotive force and put it into a circuit. Now, if this was a generator for the power grid, the circuit is going to be the grid. So the generator is going to generate electricity for the whole power grid. Or, like the example I used from, the first part of this lecture not so long ago, if you have a small little 2-stroke generator and you start that generator and it starts producing EMF, and then you plug in, let's say, an air pump to fill up an air mattress because you're out camping. That would be the circuit that generator is generating electricity for. Now, let's look at more of this simple generator. The armature is probably going to be what spins on this generator, most likely. Now, you could spin the magnet, I should say, to spin the magnetic field around the armature as well. That's fine. Most of the time, we're going to spin the armature, but you could do it either way. Just need that relative motion between a conductor and a magnetic field. Now, I say this one is probably going to spin the armature because these pole cores look like they're attached to the actual frame of this generator. Now, the frame, also called the field yoke, kind of the opposite of an egg. With an egg, the yolk is on the inside. With the generator, the yoke is on the outside. But field yoke, frame, whatever, that's the part of this generator that holds everything together. Field coils, as I mentioned, those will get some kind of electrical energy put into them. And because we have these coils wrapped around this core, these pole cores, we're turning these pole cores into electromagnets. We're lining up the domains of those those particles, those electrons and positive ions in this core. Maybe this is some kind of soft iron, some kind of material that wants to be a magnet. And so the field coils help these pole cores become good magnets. Now, the magnetic lines of force are going, they're going to want to travel throughout the frame of this generator because they don't like to travel in air. They want the path of least resistance. And this air gap, now, that's kind of a part of the magnetic circuit. I believe your module has it as the magnetic circuit or a part of the magnetic circuit. The air gap it's a part of the generator, but it does nothing. The point of it is so that this armature and the pole cores aren't touching while it spins. So the air gap is a part of the generator, but it's not a physical thing. It's just a space between the armature and the pole cores. Now, you want it as small as possible so that magnetic flux is really concentrated on these conductors. Because just like we talked about before, if you have, more conductors and more flux density and faster spinning armature here, or cutting more magnetic lines of flux by cutting it perpendicular more, you're going to make more EMF. So if we had if we had more conductors or longer conductor, as this armature spins, there would just be more conductors cutting magnetic lines of flux. If we had pole cores up here and down here as well, making it so whenever the armature spins, it's always cutting magnetic lines of flux, that would also produce more EMF. And if we spin this armature faster, that's also going to produce more EMF. Now, right now, with just these two pole cores, you can see down here, you can see it's about maybe 6 of these armature conductors, or also called armature windings, that are not cutting magnetic lines of flux at this very moment that we kind of paused and cut this generator in half and took this snapshot in time. So once again, when we're not cutting magnetic lines of flux, either because there is no magnetic lines of flux, or if our conductor is exactly parallel with the magnetic lines of flux, it's not going to be cutting them. It's not going to be, going across them, interacting with them. So here, we're making 0 volts. Now with Y, we're making some voltage. But ideally, we cut exactly perpendicular. And that's how we're going to get our peak voltage. So as that armature spins, there's going to be different levels of voltage produced depending where it is and depending how it's cutting the magnetic lines of flux. And so once again, as we rotate the armature, this whole thing would be our armature, and this would be the armature winding in this diagram. As we spin this, depending where these parts of the conductor are, depends how much voltage is produced or how much EMF is created. Both kind of the same thing, the two things I just said there. So once again, if we, just like we looked at in magnetism and electromagnetism, if we had a longer conductor, or if we had more conductor, depending how you want to think of it in your own brain, then as this spins, there would just be more conductor cutting magnetic lines of flux. And again, if we spin it faster, it's going to cut more magnetic lines of flux because of the speed it spins at. And if these magnets are stronger, or maybe there's less air gap, if they're even closer together, as close as they can be without this armature hitting it, that's also going to create more electromotive force. Now, this is it's not actually, but this is a very simple diagram to help us understand an AC generator. So now we have our brushes, and this diagram just has it, hooked up to a load. Sure, that's fine. We just need to understand how these things are going to work. Now we're going to look at a DC generator in a little bit, and the difference between the AC generator and the DC generator, it's all in the rings. It's like a proposal. It's all about the rings. If you're looking to get engaged, it's all about the rings. Usually in the culture of Canada. But slip rings, that's going to be our AC generator. And so you can write a note for yourself, or just big bold, slip equals AC, AC equals slip. However you want to remember that. And it's going to be slip rings, plural, 2 of them for this example. So as this armature spins and turns and cuts magnetic lines of flux, it's going to induce a voltage on the conductor, just like Mr. Faraday talked about. And look very closely. Now, this picture is in color. Your module is going to be black and white. But look closely at which part of the armature conductor is connected to which slip ring. That's going to matter. That's going to matter as we start to cut magnetic lines of force. So the brushes, as I said earlier, the brushes are going to brush against the slip rings, true to their name, and the slip rings are going to slip. They're going to turn with the conductor. They're going to slip past the brushes. So pretty true to their names, the slip rings and the brushes. And as the slip ring hits the brushes or pushes against the brushes, the EMF that is created or converted from a mechanical energy into electrical energy, that voltage on the armature conductor can now leave from the slip rings with the conductor connected to it onto the brushes, which then goes out to the load or out on the circuit. So let's look at that process in action. So our armature is in the same place. We have these magnetic lines of flux, these magnetic lines of force going from north to south. At this point, there is no magnetic lines of flux being cut. At sort of, if this was 0 degrees / 360, sorry, can't write sixes properly. If this was, at the top, if a circle is 360 degrees and we're up here, or 0 degrees, and then maybe we go past 90 degrees, 180, 270, and then of course back to 360. So at 0 degrees, we are producing 0 volts. We are not cutting magnetic lines of flux. They're just kind of falling through the middle of the armature. Nothing substantial is really happening. This will be known as our neutral position. So there's nothing happening in terms of voltage. And then stuff starts happening. So now it kept turning. The armature kept turning and spinning. Now on this rotation, now it's going to be cutting the most amount of magnetic lines of flux. And we're going to hit our peak right here. Now, if you remember that sine wave I've been drawing in some of the lab classes, this might start to look familiar. And if you're wondering how the path of current was figured out, it's just back to Mr. Fleming's left-hand rule. Now, hopefully this makes sense in the recording, but index finger is going to go from north to south. That's not going to change. The armature is spinning like this, if that makes sense. So it's turning like this, going from, just like this arrow was saying, which means if I'm going north to south like this and I'm going down, that means my current is going this way on this part of the armature. So just like these arrows are noting. And on this part of the armature, because it's spinning up, my current is going this way. So that's how the current is flowing in the armature. And because of where each armature conductor, or each part of the armature conductor, because of what slip ring it's connected to, so in this colored picture, the white part of the armature is connected to this slip ring, and this brown tan colored part of the armature is connected to this slip ring. So if current is going this way on this brown part, then the brushes have current flowing to the slip ring, if you want to think of it that way. And on this white part of the armature, the current is flowing away from the brushes. And once again, because we're cutting the most amount of magnetic lines of flux, we're hitting our peak voltage on the positive alternation. And then as the armature continues to spin, we hit 0 again. So if we look at our circle, once again, And the circle should start to make sense when it has, the graph has time, but it's using degrees. So it's using that because when the armature was, flat and cutting the most amount of magnetic lines of flux, it was at 90 degrees. As we go around a circle in the counterclockwise, which is just the way this armature is spinning, down here would be 180 degrees, and no magnetic lines of flux are being cut at 180 degrees. So then our current goes down to zero, or our peak voltage is down at zero. Now, because we have this hooked up to a circuit, I've kind of been using voltage and current interchangeably, but I'm doing that because we have this hooked up to a circuit, and so since we're producing EMF and we have a load hooked up, well, then we're going to get current flowing. So this could also be voltage. They don't have any values, so we don't really need to worry about the values. We're just kind of focusing on the theory and the function of this generator. So our peak voltage, or our peak current, or peak EMF production, happens at 90 degrees, and then it goes back down to zero current in this situation. My apologies if I was confusing you by switching between current and voltage. But how much we produce will be zero at 180 degrees, same as it was at 0 degrees at the top. And then you may already be ahead of me on this. Now it's going to be at the peak, but on the other end, on our negative alternation, at 270 degrees. So once again, if we drew our circle, this would be 270. But the reason it's down here at our negative peak is quite simply because of which slip ring is touching which brush. So in our armature, using our left-hand rule for generators, or Fleming's left-hand rule, whatever you want to call it, same thing's happening. So we have our finger, same thing's happening in the armature, that is. Because our finger is going from north to south, and if I'm looking at this white part of the armature, the direction of force of the conductor is going down, which means my current is going that way. And then the opposite is true over here. The direction of force of my conductor is coming up out of the page, which means current is coming down this way. But now, since the armatures have kind of flipped, now current is coming out from this slip ring, away from the brushes, and it's coming back to this brush on this slip ring. So that's how we get our negative peak current. And it would also be our negative peak voltage as well. So our current and voltage is going to alternate the same way depending on where this armature is spinning, or where it is in its rotation, if you want to think of it that way. And then when it's back to 0 or 360, we've finished making our AC sine wave. Now let's look at the DC portion or the DC generator. It's all about the rings. When you're thinking, is it a DC or AC generator? Now this commutator here, also known as a split ring. Now it is split by this insulation. And we have two brushes still, but both brushes are going to touch the commutator. So there's just one ring now. So it's a split ring. So we're going to do singular, not plural. So split ring equals DC. Split is DC. Slip rings, plural, slip rings are AC. So The way this makes DC energy is going to be quite similar to the AC generator, but because we have just this one ring, which is, each half is insulated from each other, which means one part of the armature is connected here, the other one's connected here. The reason this makes DC is, so we're making 0 volts or 0 amps, however you want to look at it, while it's at that 0 degrees position. That's still the same. We rotate through and we cut the most amount of magnetic lines of force. And we can use Fleming's left-hand rule and see that, yep, that makes sense. That current would come in here, right? That's all good. We're going to hit our peak when it's cutting the most amount, or as much magnetic lines of force as it can. Same thing here. We're back at 180, so it's making no energy. But then we hit the other half, and our peak goes back to the positive. Because of the brushes, and since it's insulated, these armatures are each going to make current and voltage in their own ways. But because the brushes touch the same spot, and we don't have the two rings, now it just stays in the positive. So instead of alternating from positive to negative, it just stays positive. So we're going to call that the direct current for our generator. And then once again, as we get back to 360, it goes back to 0. But the DC generator is just going to stay up here in the positive current or the positive voltage part of the graph. Whereas our AC, because it has two slip rings, goes from positive to negative, and then it repeats the process. So that's it for generators. As always, send me your questions if you have them.